Right, so last time we introduced the notion of infinite series, enough to see that there are some potential problems with just trying to add up infinitely many numbers and not being careful about what that means. So today, the first order of business is to define what we mean by an infinite series, what it means to add up infinitely many numbers. And then, of course, that'll lead into questions of how to actually do it, how to calculate various infinite sums. But first, definition. Our way of getting around some of the paradoxes last time is actually similar to what we did for infinite expressions. 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus dot, dot, dot. And the key was, hey, that's a limit of finite expressions. Similarly, we're going to define an infinite sum to be a limit of finite sums. So our definition infinite series A0 plus A1 plus A2 is the limit as n goes to infinity of something that we'll call Sn, where Sn is the sum of all the terms up to An. This is called a, quote, partial sum of the infinite series. We're only summing up finitely many terms. And the idea for an infinite series is to take a limit of how many terms you've added up. Now, this also allows us to talk about pathological cases. Limits don't always exist. As with any limits, so this is a limit of a sequence, right? This is just a sequence of numbers. We've been talking about limits of sequences for the last week. Anytime I ask a question about the limit of a sequence, there's 4 possibilities. The limit could converge, meaning there's a finite number. It could diverge to infinity, meaning these just get larger and larger and larger positive numbers. It could diverge to minus infinity, meaning bigger and bigger and bigger negative numbers. Or it could diverge, but not to plus or minus infinity, like oscillatory behavior or something like that. So all of those things can happen for an infinite series. One of the assumptions that got swept under the rug last time, when we were just throwing infinite series around right and left, was that they even existed. That those expressions we wrote down, like 1 minus 2 plus 3 minus 4, had some value. But actually, as soon as you write down an infinite series, there's 4 things that could happen. One of which is that it has some numerical value. Right? So we have at least sort of the categories to think in to analyze what's happening when we add up infinitely many. All right, so with this in hand, let's go back to some of the examples from last time and see what we have to say about them by thinking about partial sums and then thinking about limits of partial sums. All right, so here's a series that we saw before. And just jumping in and trying to calculate suggested that it equals 2, which is right, as it turns out. But let's try to confirm that. So this is A0. This is A1. This is A2. And so on. Note that a series is built out of a sequence, right? It's just that we put plus signs in between instead of commas. So, a section ago we would have said, consider the sequence 1, comma, 1/2, comma, 1/4. Now we're just saying, take that sequence and add them all up. That's called a series. All right, so we need to think about partial sums. The 0th partial sum is just the first term. The first partial sum is the sum of the first two terms. The next partial sum is the sum of the first three terms, and so on. And if we want to get a handle on this infinite series, we need to find some kind of pattern in these partial sums. Well, this is just 1, of course. This is 3/2. If I want to put this over a common denominator, this is 3/2, that's 6/4, 7/4. If I were to go out to the next one, it turns out that could be written as 15/8. Dot, dot, dot. So if we're trying to find this infinite series, the key question is, can I find a formula? A formula for Sn so that we can figure out the limit of Sn. Okay, our goal is to find the limit of this sequence. Another big picture point, by the way, there's two sequences involved when you write down an infinite series. There's the sequence of terms, 1, 1/2, 1/4, and 8. We're building a second sequence, the sequence of partial sums, 1, 3/2, 7/4, 15/8. And we're trying to find the limit of this second sequence that we built. Well, it'd be nice to know what the terms are. Can I write down a formula for Sn? So, do we see a pattern? Do we see a pattern in the 4 terms that we already have? Nick?
The numerators are all prime.
15 isn't prime, but they start out that way for sure. What about the denominators? One, 2, 4, 8. So that looks like powers of 2. Luke, we're going to say something about the pattern here?
Yeah, that it's increasing, but at a slower and slower rate.
Right. Yeah, so they're getting bigger. But the amount they get bigger goes down. In fact, the amount they get bigger are just these ones. So you get bigger by 1/2, and then you get bigger by 1/4, and then you get bigger by 8. So Nick's idea of looking at the numerators and denominators is something we could pursue. So this 1, 2, 4, 8 looks like powers of 2. 3, 7, 15. Not quite primes, but there's something else going on there. Yeah, Ida.
So 7 is 3 times 2 plus 1.
Yeah.
7 times 2.
So you keep multiplying by 2 and adding 1. So times 2 plus 1 is this. Times 2 plus 1 is this. Excellent. Yeah, that's right. So times 2 plus 1 would be 31 for the next, and that turns out to be right. Good. So that's a recursive definition for the numerators. Double and add 1. Double and add 1. Double and add 1. Keep going. Cool. It would be even nicer if we could have a closed form so we could see the limit more easily. But that's a great pattern to learn. So the numerators keep doubling and adding 1. What are the numerators 1 less than? 2, 4, 8, 16, powers of 2. So we've got powers of 2 on the bottom, 1, 2, 4, 8. And we have 1 less than powers of 2 on the top, 1 less than 2, 4, 8, 16, 32. So I'll just say, by looking at it for a while, it looks like Sn is, all right, the denominator is 2 to the nth power. The numerator is 2 to the n plus first minus 1. I would not expect that to be obvious. Right? Another way to see it, by the way, is to rewrite these in a different form. 15 over 8 is just a little bit less than 16 over 8. In fact, it's 2 minus an 8. 7 fourths is a little bit less than 8 fourths. In fact, this is 2 minus a fourth. This is 2 minus a half. This is 2 minus 1. So another way to write our partial sums is 2 minus 1 over 2 to the n. And of course you can see algebraically that these are equivalent. If I break this up into 2 fractions, the first is 2 to the n plus 1 over 2 to the n, cancels down to 2. And then the second is 1 over 2. So we got 2 different expressions there for the nth partial sum. Well, especially if we write it this way, we can clearly see what the limit of the partial sums is. And the limit, as n approaches infinity of Sn, is the limit as n approaches infinity of 2 minus 1 over 2 to the n. That's 2. Thus, this infinite series, 1 plus a half plus a fourth, equals 2. All right. This is an example of what's called a geometric series, which we'll come back to in a moment. So again, this is, if you just throw this down as a problem to sight read, it requires some ingenuity, but it's a very standard example. So once I induct you into the mysteries, it won't require as much trickiness. Let's look at some of the other examples that we saw last time when we were deriving all these weird notions like negative and 12 being the sum of the natural numbers, and see what their partial sums look like. So let's say 1 minus 2 plus 3 minus 4 plus dot, dot, dot. Let's think about what the partial sums do for this series. So if I call this a 0, actually, you know what, just to mix things up, I'm going to call it a 1. We can start our series at either 1 or 0. Doesn't matter too much. So my first partial sum is just the first term. My next partial sum is the sum of the first 2 terms, which is negative 1. And 1 minus 2 plus 3 is 2. Then 1 minus 2 plus 3 minus 4 is negative 2. And then it turns out the next one is 3, and then negative 3, and then so on. So if I look at the partial sums, 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, there's a rather obvious pattern in those partial sums. It would be a little bit more work than it's worth to write down an algebraic formula for the partial sums, negative 1 to the power of n plus 1 times the floor of n over 2, or whatever. Let's not worry about that. But there's a clear pattern in the partial sum. They're growing in size, and they're alternating sign back and forth, plus, minus, plus, minus, plus, minus. clearly, Sn grows in size while alternating in size. Conclusion, the series diverges. But because it's alternating in sign, it doesn't go to infinity. It doesn't go to minus infinity. It sort of does both at once. It doesn't have a well-defined single value, even infinite. Does not go to infinity, does not go to minus infinity. That's what's going on with this series. And with the, is that a question or just moving ahead?
So wouldn't it oscillate between plus or minus infinity?
Yeah, so the even partial sums go to minus infinity and the odd partial sums go to plus infinity. So we could try to slice even finer with the different types of divergence. I've sort of split up divergence into 3 types, right? It diverges to infinity, it diverges to minus infinity, or neither one. But we could split it up even finer. It diverges to infinity, it diverges to minus infinity, it diverges where its absolute value becomes infinite, but its sign can't make up its mind, and neither one. Right? We could sort of have even more categories of divergence. Yeah, so this is a, although, we could say the absolute value of Sn goes to infinity. So there's a bit more we can say than just divergence. Yeah, this phrase may be a little bit misleading. It diverges, but it doesn't diverge to infinity, and it doesn't diverge to minus infinity. Yeah, it can get long-winded. And then, the last example, the sum of the natural numbers. Right, the partial sums are 1, 3, 6, 10, ... These are all positive. They're growing in size. This diverges to infinity. So if you look at a lot of the calculations we did last time, there are things like, what if I take infinity minus something that diverges with no value? Right? Well, it's kind of gibberish, right? There's nothing we could really say about that combination. So. All right, so that's the definition of infinite series. That's a first entry point for studying. You look at partial sums, and then you look at the limit of the partial sums. Now, you may already have been able to tell from the example that we did that finding a formula for the nth partial sum is no mean feat in general. We had a sequence with a really clear pattern, and we had to work pretty hard to write down a formula for Sn. So it turns out calculating infinite series is usually hard. So I'm going to give kind of a big picture survey of the terrain for calculating infinite series exactly. It's usually impossible to calculate exactly. If I just write down some infinite series, probably can't find a closed form for the answer. And the issue is usually you can't find any nice closed form for Sn. Even if you're clever, even if you're really good at pattern matching, you probably can't just write down a formula for Sn. Because we kind of got lucky the last time. It's even worse than integration, right? Integration, there's a bunch of techniques where we can do integrals, And then there's some impossible ones. And if you have an impossible one, we kind of throw a Riemann on that. For series, even more of them are impossible. And the way you would approximate a series is you just add up a bunch of terms, right? Add up the first billion terms. It's a pretty good estimate of what happens if you add them all up. So there are 3 cases where you can find them exactly. And we'll learn those 3 cases. But we'll also spend a lot of time on the question of what if you aren't in one of those 3 cases. So the 3 cases where you can calculate a series exactly. First, geometric series. We've already seen an example. Second, not nearly as important, but we will do, telescoping series. And third, very important, Taylor series. These are related to the Taylor polynomials that we've already studied. In those 3 cases, an infinite series can be evaluated into a single closed form answer. But the rest of the time, we will have a big focus on convergence tests. We'll have a lot of attention given to the question, okay, here's an infinite series. Maybe I can't actually calculate it. Can I at least tell whether it converges or not? We've done something like this with improper integrals. We had the comparison theorem, where if you have an improper integral, maybe you can't actually do the integral, like 1 over the square root of x cubed plus 10. Maybe you can't take an antiderivative, but I'd at least like to know, is it infinite or finite? Similarly with series, actually much more the case. We'll spend probably a couple of weeks on this, just looking at ways to tell if a series converges or not. If it does converge, like I said, the next step would be throw a computer at it, add up a billion terms. But if it doesn't even converge, you're wasting your time, chunk, adding up a billion terms of a series that doesn't even approach a limit. So this is going to turn out to be where a lot of the action is for infinite series. But we'll get to that next time or the time after. For today, we want to pursue these first couple of cases where we actually can find a closed form result. All right, so the first special case worth knowing is geometric series. All right, so we'll find a geometric series is of the form some number plus c times r plus c times r squared, r cubed, and so on, which can be written in sigma notation as the sum from 0 to infinity of c times r z for some numbers c and some. All right, so the example we've already seen, write out a few examples of geometric series. One plus a half plus a fourth is geometric. The first term is 1, and r is 1/2. Okay, that's an example. Another example, 3 plus 15 plus 7/2. dot. The first term is 3. And keep multiplying by 5. Wait, did I do that right? No, it should be 375, sorry. Another example, 4 minus 4/3 plus 4/9 minus 4/27, and so on. Here the first term is 4, and r is negative 1/3. One way of characterizing a geometric series is that if you take the ratio between two consecutive terms, it's always the same. So like this divided by this is 5. This divided by this is 5. This divided by this is 5. This divided by this is negative 1/3. This divided by this is negative 1/3. This number r is called the common ratio of the series. And geometric series are precisely the ones that have a common ratio, the ratio of each term to the one before. If you're wondering about the name geometric, Euclid studied certain geometric series in the course of his geometry. It's a geometric series of 3 terms. If you take a right triangle, for example, and draw it this way, and then draw it perpendicular, it turns out that the series this has a common ratio. So that's where the name originated. Okay. So the basic result on geometric series is that the series sum C r to the n converges if and only if the absolute value of the common ratio is less than 1. In which case, we can write down its value. Over 1 minus r. Right. This may be the most important infinite series of them all. Right, so know this goal. It's a geometric series. First term divided by 1 minus the common ratio. So if we look at these 3 examples, let's see what this formula or this theorem tells us. Here, the theorem says the sum should be the first term over 1 minus the common ratio. 1 over 1 minus 1. That evaluates to 2, just like we found the hard way a moment ago. What about the second example? Common ratio 5 diverges. The third example, the common ratio is less than 1 in absolute value. So I'm going to take the first term over 1 minus the common ratio, 4 over 1 minus negative 1/3. That's 4 over 4/3, which is 3. According to the theorem, this infinite geometric series adds up to 3. Okay, let's see why this is true. Well, we need to look at the nth partial sum. So Sn is C plus CR plus CR squared all the way up to C times r to the n. And the key trick is to think about, what if I multiplied that by r? Sn times r. It's almost the same. C times r, C times r squared, C times r to the n, C times r to the n plus 1. I'm adding up a list of numbers that are almost the same as before if I just like shift the series by r. Well, I can subtract these from each other. This is similar to the tricks we did last time, but this time we're doing the tricks with finite sums. There's no paradoxes or things getting swept under the rug. It's perfectly legit algebra. So on the left, I get Sn times the quantity 1 minus r. I subtract S minus r times S. And on the right, when I subtract top row minus bottom row, almost everything cancels. I get C times 1 minus r to the n plus first. The only surviving terms are this one and this one when I do the subtraction. So if I divide by 1 minus r, I can see that Sn is C times 1 minus r to the n plus 1 over 1 minus r. That formula itself can be useful sometimes. Finite geometric series are a thing. They matter. If you study financial math, for example, this will be really important to know the effect of compound interest over a finite length of time, things like that. Trying to figure out the future value of some bond or whatever. You're going to do something like a finite geometric series. So for our purposes, what we want to do with that formula is think about what happens as n goes to infinity. This is the only n in the formula. So what happens if I take r to the n plus first power? Well, if I take a number bigger than 1, its powers grow and grow and grow and grow, right? Take a number bigger than 1, this is going to go to plus or minus infinity. So if the absolute value of r is bigger than 1, then the size of Sn is going to go to infinity. And it may or may not oscillate in sign. Depends on if r is positive or negative. But either way, the sequence diverges. Right? We could have added detail to our theorem to talk about when it diverges to infinity, when it diverges to minus infinity, when it doesn't either. But it diverges. If r is bigger than 1, this term is going to blow up. If r equals 1 in size, actually we could have an issue in this formula with a division by 0. If r equals negative 1, we're going to get this oscillating behavior. 2, 0, 2, 0, 2, 0. If r equals 1, then our series is C plus C plus C, which diverges. If r is negative 1, the series oscillates. We're going to get 2C over 1 minus r. Oh, sorry, the series is going to go C minus C plus C minus C. The partial sums go C, 0, C, 0, C, 0, C, 0. They don't approach that one, right? But if r is less than 1 in size, its powers go to 0, whether it's positive or negative. Take a number less than 1 to a huge power, it tends to 0. So if the absolute value of r is less than 1, then r to the n plus 1 goes to 0. So Sn approaches C times 1 minus 0 over 1 minus r. In other words, C over 1 minus r. All right, so geometric series are one of the rare series that we can do because they're one of the rare series where we can find a closed form for the partial sums. All right, so So if you wanted to calculate particular cases, like I said, those examples, 4 over 1 minus negative a third, or something like that. But also hold on to this in terms of the theory. When we develop our convergence tests, we look at different kinds of comparison or whatever. We'll often compare to a geometric series, just because that's one of the few things that we know. The other thing to know about geometric series, just as a point of the bigger picture of math, is geometric series have something to do with infinite decimals. So geometric series are related to repeating decimals. So as an example, let's say I want to evaluate a decimal expression like 2.537373737, dot, dot, dot. So there's this pattern, this block, 373737, that repeats forever. Expecting you to put another? No, just moving around. Cool. So one thing that we can do is write this as a sum. Okay, when you have a number written in the decimal form, this is 2.5, say, plus the first block, 0.037, plus the second block, 0.00037, plus the third block, 0.00037, dot, dot, dot. So think of that decimal as a sum. It's an infinite series. And we can write each of these as 37 times the power of 10. So let's say 2.5 plus 37 times 10 to the minus 3 plus 37 times 10 to the minus 5 plus 37 times 10 to the minus 7, and so on. What's going on with each of these. So if I look at all the terms with the 3 7s in them, that's geometric. There's a common ratio of 10 to the minus 2. Right? Every time you shift 2 decimal places, you're multiplying by 0.01, 1 over 100. So this is geometric with C equals 37 times 10 to the minus 3, or 0.037. And the common ratio is 10 to the minus 2, or 0.01, 1 over 100, however you decide to write that. So the sum of the geometric series is 0.0, well, let's try this way, 37 times 10 to the minus 3 over 1 minus 10 to the minus 2. So this is the exact value of this repeating expression. If you wanted, you could get this as a fraction with a whole number in the numerator and denominator. Right? If you wanted to write this decimal as a fraction, so this is 5 halves plus, let's say I multiplied, this is 0.99. Multiply above and below by 1,000. And what do I need, 445? So 2,200, something like this, and you could reduce it. So if you wanted to write your decimal as a fraction, the first step is to just evaluate the geometric series and then whatever finishing touches you want there. The most famous example of this with repeating decimals is the fact that 0.9999 equals 1. This causes no end of angst and sometimes argumentation in middle school. If you tell a sixth grader this, you're going to say, no, it's not. Duh, all the digits are different. Well, what this means is that we're taking a limit. If I take a limit of finite strings of 0.9s, the limit is 1. And the distance to 1 shrinks down to arbitrarily small amounts. All right, so that's it for geometric series. The second case that can be evaluated exactly and in a fluke way is telescope series. So we'll start these today. We have a little bit more on Monday. Today we'll just see a first example. All right. Throw this open. Any patterns that jump out? If I write it with a dot, 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 it means you're supposed to keep the pattern going. What's the pattern? They're all 1 over something. 2, 6, 12, 20, Jackson?
The denominator increases by 4, then 6, then 8.
Yep, so you can look at the gaps, and there's this pattern in the gaps. Another way to express it is, what if I factor these? Does anybody see how to write these as a product of two numbers? Darryl, what do you think?
2 times 1 and 2 times 3 and 2 times 6.
Also known as 3 times 4.
3 times 4, yeah.
4 times 5.
Yeah.
So let's write this as 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5. So, in fact, this could be written in closed form as taking the sum from 1 to infinity of 1 over n times n plus 1. Okay. So, that's the pattern in the terms here. But that still doesn't tell us how to add them all up. Well, here comes the bolt from the blue. And I can call this really clever because I didn't come up with it myself. 1 over 1 times 2 well, that's a common denominator. Whoops, actually I don't need to have. That's a common denominator if I subtract something with a 1 on the bottom and something with a 2 on the bottom. This would be the common denominator if I subtract something with a 2 on the bottom and something with a 3 on the bottom. So each of those terms, which I first recognize as a product, I can rewrite as a subtraction. Boom. Where did that come from? All right. Well, let's see what happens. We follow it. Why is this good?
The terms cancel.
Yeah, just about everything cancels. Minus half plus a half. Minus a third plus a third. Minus a fourth plus a fourth. Okay, all these terms cancel. In fact, the only term that doesn't cancel is the first one. So this entire series adds up to 1. The reason this is called a telescoping series, by the way, there's this type of telescope that you can sort of expand and collapse. Imagine that you're on the deck of your ship, ahoy, and then you have your telescope, and then you fold it up, right? The series sort of folds up with this cancellation until only the first term remains. Wow. All right, so this is another one of the rare cases where we're lucky enough that we can actually evaluate the series. If you're watching closely, though, I haven't quite done this problem to its full extent yet. This type of calculation is what got us in trouble last time, where things like 1 minus 1 plus 1 minus 1 plus 1 minus 1, and throw down some parentheses in creative ways. So if I want to be careful, I should find the nth partial sum and see what happens. So suppose I were to stop, right? Here's my first term, here's my second term, here's my third term. A more careful version would be to say, suppose I take a partial sum. If I stop at some finite place, there's actually 2 terms that survive, the first and the last. Right? Suppose that I just go a1 plus a2 plus a3. That's this term minus the fourth. So Sn is 1 minus 1 over n plus 1. If I were to go a1 plus a2 plus a3, it's minus a fourth. If I were to go out to a4, I'd have a minus a fifth, and so on. So the limit as n goes to infinity of Sn is, because this term goes to 0. One of the key criteria for running under the hood for a telescoping series is the terms had better go to 0. If the terms don't go to 0, the series diverges. So, 1 minus 1 plus 1 minus 1 plus 1 is telescoping, because look at all the cancellations. But this is the kind of thing where we get ourselves in trouble. If I were to do something like 1 minus 2 plus 2 minus 3 plus 3 minus 4, that diverges. I wouldn't want to just say it's 1 because the other terms cancel. That's the kind of shady business that got us in trouble. So if we do things out carefully, here, or here, or here, the crucial difference is these terms that are canceling each other are also going to 0. If that doesn't happen, you can't telescope and get it converted. All right, so next time we'll look more systematically at how to find expansions like this one. These are a series of telescopes, and then we'll go on to the next point of theory after that. Quiz Tuesday, right? So it's going to include this and